I'm just going to talk about concavity and rates of change. So remember, the second derivative, so concavity, measures how the first derivative changes. The greater the magnitude of the concavity then, the faster the rate of change changes. So here's a curve. Point P, at that particular point, we know the first derivative is greater than 0. Curve's increasing. We also know that the second derivative is less than 0 because it's concave down. So as we move further to the right, then the rate of change is getting slower because that slope would get shallower and shallower. So it's increasing at a decreasing rate. Right? So yes, the function is increasing, but the further we go along, the rate that it's increasing is getting slower and slower. So it's increasing at a decreasing rate. Okay, Q. At that particular point, we now can see it's now decreasing. It's concave down. So here we go. This one is decreasing at an increasing rate. So this is where you've got to be careful. Just because the second derivative is less than 0 does not mean it's moving at a decreasing rate. It all comes down to which direction. See, if they're the same sign, it's like saying you're getting faster. So because they're both negative, it's decreasing, but at an increasing rate. It's getting faster and faster. Whereas the other one, they're in opposite directions. So it's increasing, but at a decreasing rate. We could have something like this. There's R. It's still decreasing, but now look at the concavity. The concavity is concave up. So that one would be decreasing at a decreasing rate. Again, the signs are in opposite direction. And that gives us the fourth case over there at S, where it's increasing and it's concave up. Signs are in the same direction, so increasing at an increasing rate. That is what I was talking about yesterday about deceleration. So when acceleration was in the opposite direction to velocity, you're actually slowing down. So it's the same idea. If the signs are in the same direction, then it will be at an increasing rate. If they're in opposite directions, it'll be at a decreasing rate. So let's have a look at this little graph here. It's an unusual graph, but there you go. It's petrol consumption versus population density in 22 different cities around the world. So at less than 20 people per hectare, people depend more on their cars for transport. And there's going to be little public transport. So you're out of the CBD, you're out in, maybe you've gone past the Blue Mountains, that sort of area. But what could be concluded about petrol consumption as the population density increases? And so we can see the curve there. Well, it's decreasing at a decreasing rate, right? Because it's concave up, so the second derivative is positive, but the first derivative is negative because it's decreasing. Opposite directions, so it would be decreasing at a decreasing rate. Temperature. So how does temperature change during autumn? Of course, first of all, you've got to remember which 3 months are autumn. We're in Sydney, so we know we're okay. And of course, autumn is, when does it start? It starts March, April, May. Okay, so at the start of autumn, so it starts in March. At the start of autumn, we're decreasing at an increasing rate because the first derivative is negative and it's concave down, same direction. However, during autumn, that rate slows down. By the end of autumn, March, April, May. So end of May, beginning of June, we'll notice, hey, the graph is now concave up. It's still decreasing, but it's concave up. And so now it's decreasing at a decreasing rate. Now, if you think about that, just actually think about what happens as we move through the year, the temperature does start dropping quite dramatically at the start. Well, it used to. Here we are in April and it's still reasonably warm. But normally what should happen is the temperature drops, and then as we get further in, closer to winter, it's still dropping, but not as quickly. Here's a relevant one. On March the 22nd, this is from a couple of years ago, the Prime Minister announced stage 1 shutdown restrictions in order to slow down the rate of new cases. There's the graph that 2 years ago we were all obsessed about. Now we don't give a damn about it, but there it is. But that was the graph going through 2 years ago, starting at, you can see in January, going through to the 25th of March. Now, at the time, you remember they said it took about 5 to 6 days for symptoms to show up. So do you think the measure of the stage 1 shutdown has been effective? Okay, well, 5 days later would be the 27th of March. Remember, March 27th, 22nd, it was announced. So if you look at the 27th, the cumulative cases curve appears to inflected. And that's what you're looking for, really, is you want the inflection point, because it's going to change from concave up to concave down. Remember, I think what was the phrase they were using back then? They want to flatten the curve. Flatten the curve. That's what they talked about in society. Mathematicians, we knew that to be, yeah, you're looking for an inflection point because it's going to go like that when it inflects. But that's effectively what we want to see here. Is it inflecting? Sure, it's a judgment call, but when I look at that curve, it does sort of appear to me it's changing from concave up to concave down. And so, yeah, it would suggest that, yeah, sure, the number of cases are still increasing, but now it's increasing at a decreasing rate. So, yeah, it probably was an effective measure at the time. And at the time, little did we know what was to come, hey? All right. So, as I said back then when I wrote this example, it's still very early, but yes, it does appear that those measures were effective. Well, they were, sort of. Okay, 90.